Hi there! Greetings from Osaka, Japan. Welcome back to the Logic of Risk. In this episode, we finally start talking about risk measures in a more technical way. And to do that, we need to introduce statistical moments. Ready? Then let's get going, but don't forget to hit that like button and recommend the podcast to anyone who might enjoy it. Moments are fundamental tools for understanding how a random variable behaves and, for us, for quantifying risk. Under the broad label moments, we can gather a whole family of measures you probably already know or have at least heard named before. The different kinds of means, from the plain arithmetic to the harmonic, variance, skewness, kurtosis, and many combinations or generalizations of these ideas. The point of moments is to answer key questions in risk management. What is the average risk of a given choice? Are we facing a concentrated risk or something more volatile? Does the phenomenon we are studying have fat tails that can generate extreme events, or thin tails that rarely do so? Does it satisfy the catastrophe principle or not? Being able to say something informed about these questions and many others matters to us a great deal. Like every statistical tool and every risk measure, moments come with usage limits. It helps to know, for instance, the difference between a theoretical and an empirical moment, and to be clear on what a particular moment can actually tell us and, above all, what it cannot tell us, no matter how much we wish it would. Remember the crushes we had as teenagers when we dreamed that the person we liked would say certain magic words, but they never did. Moments often behave exactly the same way. Life can be so unfair. Seriously now, we can discuss moments on several levels. We will begin with intuition and only later introduce formal definitions if they are really needed. As I've said before, I'm not going to spend several minutes chanting something like the definite integral over the support or capital X of x f of x dx. That is not what we need to grasp the expected value of a continuous variable. We can do it in other ways and save the formulas for the moments when they matter. Moments are quantitative measures that help us capture the behavior of a random variable. In many situations, they let us understand more clearly what a distribution function or its corresponding density implies, and they let us detect fundamental traits in the data we have on hand. The first step is to distinguish theoretical moments from empirical ones. The theoretical moments of a random variable can be computed, sometimes easily, sometimes with effort, using standard mathematical tools once we know explicitly one of the functions we have discussed in the previous episodes. Suppose, for example, that I know or someone tells me that my x follows an exponential distribution. I can sit down with paper and pencil, solve an integral, and get whatever moment I'm interested in. If I'm lazy, I let some computer algebra system crank out the result, while I sip coffee. Yet, theoretical moments can fail to exist for certain random variables. For some parameter settings of the density function, we simply can't obtain a finite value for a given moment of interest. Fortunately, the list of random variables whose moments might be missing is limited, and that is a relief. The catch is that such variables, with the Pareto distribution as a classic example, are everywhere, and they often describe phenomena that worry us. Financial losses and profits tend to follow a Pareto-like pattern, as do damage figures produced by floods, earthquakes, and similar events. The non-existence of theoretical moments creates serious headaches in risk management. problems we will tackle after we introduce the main moments in a few episodes from now. Empirical moments, on the other hand, are computed directly from data. A random variable is a theoretical mathematical representation of a real-world random phenomenon. By collecting observations, we can check whether a theoretical model we have in mind works, or craft one from the data themselves. When I compute the sample mean of my observations, their standard deviation, or anything of that sort, I'm calculating empirical moments. To a statistician, the data we collect are often a manifestation of an underlying random mechanism described by some variable and can be exploited to draw inferences about the phenomenon of interest. Imagine I think human height is well approximated by a Gaussian random variable with a certain mean and standard deviation. I can collect height data, check whether they look compatible with a Gaussian distribution, for instance whether they are symmetric around their mean, and extract precious information. For men, an average of roughly 171 centimeters, for women around 160 centimeters, both with a standard deviation near 6 centimeters. But note that computing empirical moments does not require already having a theoretical model in mind. A tricky and crucial point: empirical moments always exist, in the sense that if I have enough data, I can always compute them. The hitch is that sometimes they make little sense, less inferential and predicted value than used toilet paper, namely when the corresponding theoretical moments fail to exist. We will return to this issue quite soon. Besides the theoretical empirical split, we also speak of simple moments, central moments, and standardized moments. Simple moments describe how a random variable behaves on average, either in theory, based on a model and ignoring data, or empirically, looking at the data. The best known example is the arithmetic mean, plain or weighted. Also in this group are the moments you get by taking the mean of transformations of the variable, the second simple moment, the third, the fourth, the fifth, and so on, plus the geometric and harmonic means. Central moments measure how a variable behaves relative to its own mean. Does it condense tightly around the mean? Does it spread out, and if so, how? Does it disperse smoothly or form little clumps of values which we will call clusters? Variance belongs here, and so does the standard deviation, the square root of the variance, along with less famous but very useful quantities like the third central moment, sometimes called absolute skewness. Central moments can often be obtained conveniently by combining simple moments. Standardized moments are nothing more than central moments divided by powers of the standard deviation. In statistics, standardization usually means dividing some quantity by another, often, but not always, the standard deviation or a function of it, to make results more comparable. For now, just take my word for it. The most famous standardized moments are skewness and kurtosis. There are other families of moments, but it's too early to tackle them. We don't need to throw every stack on the grill at once. What I want to teach, if you have never seen them, or refresh if you already have, is how to compute simple moments. Let's start with the mean, the one everyone knows. Suppose 5 people I know weigh respectively 70, 75, 66, 86, and 59 kilograms. If I ask for the group's average weight, you add the numbers 70 plus 75 plus 66 plus 86 plus 59 equal to 356, and divide by 5 the number of people. arriving at 71.2 kilograms. That's what we call the simple arithmetic mean. In the simple arithmetic mean, each observation carries the same weight. And forgive the pun, given the example. All you do is add every observation and divide by how many observations you have. But what if some values occur more often than others? Or, just as important for us, are more probable? In that case, we switch to the weighted arithmetic mean. Imagine our example changes a bit. There aren't really 5 people, but 7. 3 of them weigh 70 kilos. You could, of course, keep the old method and add 7 numbers, or you can speed things up, especially when the numbers get large, by writing 70 times 3 plus 75 plus 66 plus 86 plus 59 and then dividing by 7. That is equivalent to writing 70 times 3 over 7 plus 75 times 1 over 7 plus 66 times 1 over 7 plus 86 times 1 over 7 plus 59 times 1 over 7. That is, multiplying each observation by its weight, its relative importance, its frequency within the group. The value we obtain is approximately 70.86 kilograms. Another example. A one-year investment based on supposedly reliable historical data, and if any financial advisor praises reliable historical data, stand up and walk out, can yield plus 40% with probability 5%, plus 10% with probability 55%, minus 5% with probability 30%, and minus 10% with probability 10%. I ask you, what average return should we expect? First, you verify the probabilities sum to 1, that is 100%. If they did not, we would be dealing with uncertainty, not mere risk. In that case, we would have to put the pen down and ask for clarification or go away. Let's see. 5% plus 55% plus 30% plus 10% equal to 100%. Good. Having verified that, we do nothing more than add the returns, weighting each one by its probability. 0.40 times 0.05 plus 0.10 times 0.55 plus, in brackets, minus 0.05 times 0.30 plus, in brackets, minus 0.10 times 0.10. Multiply, add, and you get 0.05, an expected return of plus 5%. Note the adjective expected, which indicates something that hasn't happened yet, but that, on average, we might look for in the future, if the past is reliably informative, meaning it contains enough useful information to make sensible forecasts. In probability theory, a weighted arithmetic mean whose weights are probabilities is called the expected value. More precisely, expected value is the official name for the theoretical weighted arithmetic mean, where the probabilities come from a specified model or assumed distribution, while in the empirical realm we usually say simply mean. When you say mean and don't add an adjective, geometric, harmonic, and so on, people generally assume you are talking about the arithmetic weighted mean. A classical theoretical illustration is the Bernoulli random variable, which equals 1 with probability p and 0 with probability 1 minus p. Its theoretical weighted mean, the expected value, is 1 times p plus 0 times, in brackets, 1 minus p, that is, p. Here is a neat surprise. In a standard Bernoulli random variable, the quantity p isn't just the probability of success, that is, of observing a 1. It is also the variable's expected value. If you are more mathematically inclined, this will look trivial. We just took the expectation of an indicator of an event, so we got the event's probability, but for everyone else it is worth remembering. The expected value, or weighted arithmetic mean, if you prefer, is the simple moment of order 1. Written symbolically, the expected value of a random variable x appears as capital E of x, where capital E stands for expectation or expected value. Simple moments of higher order, second, third, fourth, fifth, and so on, are obtained by raising each outcome to the corresponding power and then taking the weighted arithmetic mean of these new values. Let's return to our investment. The possible returns are plus 40% with probability 5%, plus 10% with probability 55%, minus 5% with 30%, and minus 10% with 10%. Take each outcome and square it. 0.40 squared is 0.16. 0.10 squared is 0.01, minus 0.05 squared becomes 0.0025, and the minus sign vanishes, and minus 0.10 squared is 0.01. Now multiply each squared value by its original probability. Super important, the probabilities stay untouched. 0.16 times 0.05 plus 0.01 times 0.55 plus 0.0025 times 0.30 plus 0.01 times 0.10. Summing these, we get 0.01525, about 1.5%. This is the simple moment of order 2, also called the second moment. As you can see, it is always positive. Every outcome, even the negative ones, is squared, and we multiply only non-negative numbers, that is, squared outcomes and probabilities. For the simple moment of order 3, or third moment, you would cube the outcomes before applying the weighted mean. For order 4, you would raise them to the fourth power, and so on. The corresponding probabilities always remain exactly what they were. Never ever raise probabilities to a power. Higher order simple moments are very helpful in revealing notable properties of a random variable, or in the empirical setting of a dataset. They also come in handy for quickly computing certain central and standardized moments, as we shall see. In the next episode, we will make a little trip back to the first 30 years of the 20th century. In papers by leading probabilists like Kolmogorov, Nagmo, De Finetti, and Chisini, we will find a fascinating and useful way of looking at the mean, one that will provide valuable tools for our risk analysis. See you next time. Take care. Ciao ciao.